Okay. So today we are starting our last two lessons on inverse trig functions. We're going to kind of go through those pretty quick, and then just applications of trigonometry. So we've all kind of seen some of these ideas before. We're just putting a nice neat bow on this. So inverse sine function. Give the definition of the inverse sine function. This is the function that undoes sine. So there are two ways to write it. We can write it as sine inverse. We're putting a little -1 up there, or arc sine. It does not matter which you choose to use. I think the book, is particular to using the word arc sine or arc cosine or arc tangent instead of like sine to the -1 power, but both are interchangeable. Actually, I have not double checked. Let's double check this on the Desmos calculator right now. If I type in the word arc, if it also works, because if I go into the keyboard and go into functions under trig, we see them all listed with the -1. It should work if I did like the arc sine of like pi over 2. Yep. Wait, undefined. Well, oh, sorry, went the wrong way. Arc sine of 1, that's the same decimal as pi over 2. So unit circle is going to be helpful for this as well. So actually, let me pull up my filled in unit circle from the 2.2 notes as well. So I had that opening up right here. Perfect. So Desmos will let you type in arc sine, or it will also let you type in sine to the -1. Now the domain is really tight, because if you think about the range of sine was only going from -1 to +1. If I'm doing the inverse of that, that means now the domain is between -1 and 1, and my range is between -pi over 2 and +pi over 2. So here they want the exact value of the arc sine of -1. So when I look, I see -1 listed right here as a y value on the unit circle. That's at 3 pi over 2. However, when we look at where arc sine is defined, 3 pi over 2 is not in there. So here what I'm going to say is, oh, I just went in the negative direction here. So instead of calling it positive 3 pi over 2, in the negative, that'd be a -pi over 2. So this exact value is -pi over 2. Okay, I'm not going crazy. I spelled that too. Okay, cool. We're all here with the same reality. Glad to know that. So again, if I did arc sine of -1, I put an extra a in front. I don't want that. I get this. Now, it's not giving me that exact value, so that's where I'm going to utilize the fact that I know the unit circle and realize that if I did -pi over 2, that is the same value. Wrong thing. Oh, there are the notes. Okay. So arc cosine, exact same idea. So I'm looking for the arc cosine of 1/2. Now, cosine, again, the domain is between -1 and +1. However, the range is out from 0 to pi. The nice part about arc cosine or inverse cosine is I'm just going to look at the unit circle. I don't have to worry about that backwards direction. So here with this, I'm looking for when remember cosine is my x values. I realize my x value reaches 1/2 right here. So that's going to be pi over 3. So that's the exact value is pi over 3. Again, if I put this into Desmos, the arc cosine of 1/2, we get this weird looking decimal, which I don't recognize right away, but if I were to type in pi over 3, we get the same decimal. So that's me utilizing that unit circle to get that. So that's where, again, this memorization of the unit circle, I know I had no way to fully hold you accountable to memorizing it, but that's where this comes in handy as well. Because actually, if you had the unit circle memorized, you could just be like, oh, wait, cosine, that's my x values. My x starts at 1, so that's going to be √3 over 2, √2 over 2. Then finally, I get to 1/2. So I could be like, oh, that was pi over 6, pi over 4, pi over 3. Tangent is very similar. Again, it is actually defined, though, for all real numbers. Because if you remember the tangent graph, that had those asymptotes going on. So like if I look at the graph of the tangent of x, we see it going down forever here and up forever here. So that's why that one gets to be defined across all real numbers. So again, I'm going to just try and utilize some of my unit circle here. So I know that tangent is defined as sine over cosine. So if it's at √3, if we want the inverse tangent of √3, what's happening here is basically I know that's like saying √3 over 1, but it actually could be like √3 over 2 over 1 over 2. So I'll go look for where my y value is this, and my x value is this on my unit circle. So where that happens, my y is √3 over 2, my x is 1/2. That's happening again at pi over 3. Again, we can type it in as the arc tan of 3. I'm just going to do to the 1/2 power because, oh, I had that up. But yeah, we're getting that same value for pi over 3. Okay. Here with this, they're asking us to round these to decimals. This is easy. Look, actually, I know this one already is undefined because the number inside of there is bigger than 1. So for arc, sine, and cosine, you need to have numbers inside there between 0 or -1 and +1. So already I know this is undefined, but for A, if I'm just given that as a decimal, I don't know where that decimal is on the unit circle. I'm just going to have to type it in the calculator. So it was arc cosine of 0.85. And that gives me 0.5548. So 0.5548. And then again, I already told you the arc sine is undefined. However, let's confirm that with Desmos. If I do the arc sine of 3.1415, whoop, one too many decimal points. It tells me that it's undefined because again, arc sine, we can actually look at these graphs. Let me turn off the graph of tangent. If I did the arc sine of x, we get this little sliver of a graph. Same with arc cosine. So arc cosine gives me that little sliver. And arc tangent is not such a little sliver, as we'll see. Arc tangent kind of looks like a sideways cubic function, or actually a cube root function would be a better way to describe that. So here with this, now there are some important stipulations for this. Basically, if I say the sine of the arc sine or the arc sine of sine, they undo each other, they cancel out. However, our x value needs to be between -1 and +1. And then for arc sine, our y value. So for the first group, this x value just has to be between -1 and 1. For this group, my y value has to be between here, technically for these properties to work. But all they're saying here is cosine undoes arc cosine undoes cosine. Same with sine and arc sine, same with tangent and arc tangent. So we got one last problem or two last problems to do here. So it says the arc sine of the sine of 3 pi over 4. So unfortunately, 3 pi over 4 is not inside of this range. However, I'm going to show us how we can actually still do something with this. Well, technically, it's not going to be that. Actually, no, that's just not possible. We can do a little something with it, but it's not going to be a straight canceling. So the sine of 3 pi over 4 is equal to, let's see, at 3 pi over 4, that will be positive √2 over 2. Again, I'm looking at my unit circle there. Y value of 3 pi over 4 is √2 over 2. So what I can then think of it as is now the arc sine of √2 over 2, and that's actually going to give me just pi over 4, because again, where is it positive? I'm only looking in these areas here, so it actually ends up being positive there. We notice that's reflected straight across the axis. So that's why I'm saying √4 over 4. That one was not an exact, hey, they just cancel out. However, the next one does fall into those parameters, because if I do the cosine of the arc cosine, just as long as that x value is between -1 and 1, it just cancels. So that's all that's happening here. So that will be equal to 0. So I think I cut down this homework a little bit for you guys. I just forgot to erase it on here. So again, we can quickly check those with Desmos. We had the arc sine of the sine of 3 pi over 4. And again, if I do pi over 4. That's, let's say, decimal. And then if I do the cosine of the arc, cosine of 0, that's 0. So let's get into our last section now. Not seeing any questions in the chat. You guys physically here look like you're getting it. So let's take a look here at applications. So I kept my drawing here just because I did a halfway decent drawing. I didn't want to have to redraw it. That's good for me. I'm just saying. Yo, and you're honestly with these, your drawings don't have to look good. They just need to convey the information. So a ladder is leaning against a house that reaches 24 feet up the side of the house and makes a 60-degree angle with the ground. How far is the base of the ladder from the house? So the base of the ladder would be here, or from the base of the ladder to the house would be right here along the ground. So I'm going to call that unknown X. 24 is my opposite side. X is my adjacent side. So I think back to SOHCAHTOA. Oh, tangent uses opposite over adjacent. So that's what I'm going to utilize here. I can say that the tangent of 60 is equal to my opposite side 24 over my adjacent side X. So in order to solve this, basically, I'm giving you a shortcut here. What we can do is multiply both sides by X, and that would give me X times the tangent of 60 equals 24. Then we would divide by the tangent of 60. When you have your variable in the denominator like this, essentially you can just swap these around. So that tells me X is equal to 24 over the tangent of 60. That I'm just going to have to utilize a calculator. Key here is Desmos loves to default to radians. You could change 60 into pi over 3 radians and get your answer that way. But I'm going to also show us we can just switch our units to degrees. And that's what we're going to do. So we're going to switch the units to degrees, just do 24 over the tangent of 60, and that will give us the distance. Getting somebody in the chat. I think you might still be in radians because we should be getting an answer smaller than 24. Let's see. Yeah, so I need to hit the wrench here and switch to degrees. And I'm doing 24 divided by the tangent of 60. Oh, 34, yeah. I was about to say being 19 feet away didn't seem, well, that's still kind of far away, but being a little less than 14 feet definitely seems a little more reasonable than the other way. If you aren't in the right mode, if we're in radians, yeah, so somebody in the chat did put the answer as 74.99. My suspicion was right. They were working in radians. We just need to hit the wrench and flip it over to degrees. And we get 13.86. Round to 2 decimal places here. So it will be X equals 13.86 feet. Seems a little far away from the wall, in my opinion, like having a ladder like 13 feet away from where it is. But hey, it's getting the job done, and that's okay. With problems like this, try and use some real world context too. And think about if I'm putting a ladder against something, should it be kind of close to the wall or far away? Like I said, I'm thinking 13 feet. That seems a little further away than I expected, but not unreasonable. So here with this, we're talking about the idea of bearings. So this is a way to do this. Use to give directions in surveying navigation. Bearings measure the acute angle from either north or south. So a bearing of north 70 degrees east is facing north. We move 70 degrees to the east. So that would be right here, 70 degrees. So that is the idea. So if I'm saying north and then it goes east, go to your north line and head that many degrees eastward. If it said north, that gave a degree west, then we go westward. Same with south. You're facing south, and then you'll go up and up. Let's take another look here. So write the bearing of this. This we just have to be careful with here. This is 30 degrees from west, right? Which means if I'm going from south, that'd actually be 60 degrees here, right? So this is a south bearing, goes 60 degrees to the west. Make sense? Okay. So, talking about some other applications. Harmonic motion is an awesome application of trigonometry. So whether we're talking about the vibration, oscillation, or rotation of an object under ideal conditions. Now, when you start talking about physics, things like friction might start taking over. So those ideal conditions might not be there. So you might have some dampening factors that slowly shrink the curve. But under ideal conditions, such that the object's uniform and regular motion can be described as a sine or cosine function, is called simple harmonic motion. So ideally, a spring, if I pull it down and let it go, it keeps going up and down. That's the idea of simple harmonic motion there. A point that moves on a coordinate line is said to be simple harmonic motion if the distance from the origin at the time t follows either a times the sine of, oh my gosh, I'm forgetting what Greek letter that is right now. We'll just call it w times t, or cosine, where a is the amplitude. So if I pull it down 2 feet from its starting position, that would have an amplitude 2. And then the period will be 2 pi divided by w, and the frequency is literally just the reciprocal of that. So here with this, give the maximum displacement of this. The maximum displacement is just the amplitude. The amplitude here is 3. So they gave us this equation for simple harmonic motion. I just pulled the amplitude from there. That is going to be 3. I'm just going to call it units because they did not describe to me what my units are. That could be feet, that could be meters, that could be inches. I don't know right now, but tell the frequency of the harmonic motion. So remember, frequency is W divided by 2 pi. So that will be, so my W is 1/2. So that's going to be 1/2 divided by 2 pi. I don't like how that's written, so I'm going to rewrite this as 1/2 times 1 over 2 pi, giving me 1 over 4 pi. And so that's how far it's going to or sorry, I'm at frequency, not period. So the frequency is how many cycles it goes through in 1 second. The period is how long it will take to go through one cycle. So the period will be 2 pi over 1/2, which is 2 pi times 2 over 1, which is 4 pi, which is also the reciprocal of my frequency. My frequency was 1 over 4 pi. Take the reciprocal of that, that'd be 4 pi over 1, or just 4 pi for my period. So again, I think I cut down the number of problems here just because I'm giving you 2 assignments at once. It's the very last assignment of the marking period or of the class even, or homework assignment. We still have our last test on this, on trigonometry. So here with this, that's the applications. That's the big parts of our trigonometry unit. Yeah, and we'll go from there. So that's what our last test is going to be on. So let me stop recording.